We were looking at this question related to uniform random variables where we had x is uniformly distributed with parameters a is 3 and b is 6. And we talked about how the PDF of x is, right, it's equal to 1 by b minus a is 1 by 6 minus 3 is 1 by 3. For x greater than equal to 3, less than equal to 6, 0. Otherwise, whenever you're looking at any random variable, whether it's discrete or continuous, it's very important to keep in mind the values for which it is and the values it takes, right? So in this case, note x only takes values. Before we actually do the question, it's important to keep this in mind between 3 and 6, where its PDF is non-zero. Because a continuous random variable takes values where its PDF is non-zero, right? So it's very important, regardless whether you're looking at a discrete or continuous random variables, to always note what values does the random variable take on. So you do it for both discrete and continuous. And for continuous, the values it takes on is where its PDF is non-zero. Values does the random variable take on. That this is important to remember. Now, why is this important to remember? We've already done part A and B. Let's do C. We want to find the probability that x is less than 4, right? So we want to find this. Now, there are actually two approaches we're going to use to solve this. One is we're going to do it similar to part B. We can do it similar to part B, the way it's done in part 1 of the series. In part B, that's one way, right? We can do it similar to part B. So we want to find probability. Okay, this should not be less. This should actually be probability. We want to find x is greater than 4. We could do less as well, but we want to do greater than 4. So we want to find probability x is greater than 4. So now probability x is greater than 4. I know I can write it as probability x is between 4 and 6, right? So we can write it as probability x is between 4 and 6. Why can we write this? Because x takes on values between 3 and 6, right? This is why, again, it's important to keep in mind the values the values random variable takes on. Where for continuous random variables, we know that it takes on values which PDF is non-zero. So the fact that we know it takes on values between 3 and 6, we can write probability x is greater than 4 as probability x is between 4 and 6, right? So that's what's important to keep in mind. What values does your random variable take on? So then we can write this as, we know okay, area under the PDF gives us a probability, and we can find area under the curve using integral. So we can just integrate this PDF from 4 to 6. Then you can find the probability that x is greater than 4. And this would just be 1 by 3. And then this would just be x, the 4, 6. And this would just be 6 minus 4 divided by 3 is 2 by 3. So this is how we did in part B. We also talked about in part B, another way we could do it was that we could just look at the graph of the PDF. As we know, area under the PDF gives us probabilities, and the area under the graph, area under the PDF of a uniform, area under the PDF of a uniform random variable is just the area of a rectangle. This is something we looked at in part A. Right, so it's just a rectangle, and the area of rectangle is easy to find. So we didn't even have to do integrals. This is how we do its PDF in part A, where we had fxx here, small x here, and this was 3, 6, and this was 1 by 3. So we know area under this PDF is just the area of a rectangle, and this is giving us probability. So we could just do it like this also, right? For instance, we know we want to find the probability x is greater than 3. So we want this to be greater. We were talking about this. So x is greater than 4. So x is greater than 4 is this area, right? So this area under the PDF is the probability x is greater than 4, which we know is the same thing as the basically the probability x is between 4 and 6, so it takes values between 4 and 6. Now we know for the area of this rectangle, this is 1 by 3, right? We know this is 1 by 3 and we know this is 6 minus 4, 2. So we can find this as 1 by 3 times 2 is 2 by 3. So like we talked about, for uniform random variable, you can find probabilities related to that either using its PDF where you integrate it over whichever interval you want to find the probability that uniform random variable lies in, or you can just look at the graph of the PDF of that uniform random variable, because its area under its PDF is just the area of a rectangle, and finding the area of a rectangle is easy. However, we could have done part C in another way as well, using a property. So one way to do part C was to do it in a way similar to how we did part B, either integrate the PDF or look at the graph of the PDF. Or another way to do it is part B is to use a property of uniform random variables, right? Let's look at what property you're talking about. Note for uniform random variable. So uniform, so we're talking about uniform random variable. Note for uniform random variable X. Let's just talk about a uniform. I'm sorry, why am I writing this? X is a, so let's look at this property that for uniform random variable, right, that has parameters a, b, right, the probability of lying in an interval. So the X is uniformly distributed with parameters a and b. The probability of lying in an interval, which is a subset of AB, in an interval, which is a subset of AB, right? So we know it takes on values in that interval. We know uniform random variables PDF is non-zero in the interval AB. So the probability that lies in some interval, which is of lying in an interval, which is a subset of AB, sorry, AB depends on the length of the interval. What does this mean? We look at that and how we apply it. Depends on the length of the interval. Right? So the probability it lies in any interval, which is a subset of AB, a subinterval, depends upon the length of the interval and not where the interval is. Let's see where we apply it and not where the interval is. So here in part B, we were looking at this interval, the intervals 3, 5, right? In part B, we're looking at this interval. The probability x is less than 5. We know this is the same as the probability x is between 3 and 5, because again, it takes values between 3 and 6 in this case, right? Because this is where its PDF is non-zero. So the interval 3, 5, which we were looking at it in part A, and 4, 6, which we were looking in part C, because the probability is greater than 4, is the probability is between 4 and 6, because again, it takes values between 3 and 6, have same length, right? They have the same length. Right, so these are the same length intervals. Both of these intervals, 3, 5, 4, 6, are subsets of the interval 3, 6, right? And the length for this we know is 5 minus 3 is 2, and the length for this is 6 minus 4 is 2. So because both of these intervals have the same length, right? And we said the probability of lying in an interval, which is a subset of AB, any subinterval of the interval over which the uniform random variable is defined, depends upon the length of the intervals. What this means is that intervals, that subintervals that have the same length, the probability of the uniform random variable lying in them would be the same, right? So this essentially means that, just a second, this essentially means that the probability, okay, sorry, so the probability that x is between 3 and 5, which is what we found in part A, is the same as the probability x is between 4 and 6, right? And this we know is 2 by 3 from part B. So from here, we know the probability, without even finding, using the PDF or you looking at the graph of the PDF, we know the probability that x is greater than 4 and less than 6 is just 2 by 3. And what we calculated earlier using the PDF and looking at the graph was 2 by 3, right? And this was not a coincidence, right? Because for uniform random variable, the probability lies in any interval, which is a subset of the interval over which the uniform random variable's PDF is non-zero, i.e. AB depends upon the length of the interval, not where the interval is located. Because both of these intervals, 3, 5, and 4, 6, have the same length too. The probability that the uniform random variable lies in these intervals is the same. So we didn't have to calculate this probability for C. The probability for C would have been same as B because of this property, right? So we could have done this without doing any, using the integrate as well. Similarly, without doing any calculation, without doing any calculation, we know probability of x, we know probability of x lying inside any interval, with length 2, which is a subset, lying inside any interval, which is a subset with length 2, which is a subset of of 3, 6. Again, any interval which is a subset of this has length 2 is 2 by 3. Right, so I could also say the probability that x is between 3.5, 5.5 is equal to the probability x is between 3.25, 5.25. All of these are 2 by 3. We don't have to do any calculations because based on this property uniform random variable, we know the probability that x lies in any interval which is a subset of 3, 6. Why 3, 6? Because x was defined as uniform with these parameters 3, 6, right? So its PDF is non-zero with this, right? So the probability lies inside any interval which is a subset of 3, 6 with length 2 is 2 by 3 because that's what we calculated in part B. So that's how we could have done part C either similar to part B. Okay, you integrate the PDF or look at the graph of the PDF, or just use this property of a uniform random variable that for any uniform random variable that has parameters A, B, the probability that lies inside any interval which is a subset of AB depends upon the length of the interval, not where the interval is located, right? And this is how we applied it here.